welcome to the next lecture on control unit design of control unit part 2. We will continue from where we left in the previous lecture. So, in the previous lecture we have seen a single bus architecture, we have seen also a multi-bus architecture. Now, we will be specifically looking into how we can perform an operation. So, for performing an operation, what is actually required? Let us see the organization of a register. A register is used for temporary storage of data. So, in this particular register, we actually store data. And now we are saying that we require the data. When we are doing add R1 plus R2, we require the data from R1 to be available in ALU. We require the data R2 to be available in another input of the ALU. In such cases, the data from this register needs to be moved out through this bus and it reaches the ALU. And in the same way, after the operation is performed, the data must be brought in to a particular register. So, a register Ri typically has two control signals. What is that? R1 in and R1 out. What is R1 in? You see the arrow. R1 in meaning something is coming into R1, Ri. So, data available from the data bus will be available to register Ri through the control signal Ri in. Next is, we also sometimes require the data from register to come out of this bus and then go to somewhere else. So, what is the control signal required for that? The control signal required for that is Ri out. So, Ri out will place the value from this particular register Ri into the bus. So, two signals are very much important. Ri in, that will make the data from bus into this particular register. Ri out, that is used to place the data stored in the register on the bus. So, from the register the data will be put into the bus. So, from the arrow you can easily make out. Input and output lines of the register Ri are connected to the bus via control switches. So, basically these are some switches. So, these switches are made on and off to do the particular function. So, what we have to do? We have seen that Ri in is used to load the value here and Ri out is used to take the value from the register and put it available in this bus. Now, let us see, when Ri in is 1, that means Ri in is active, the data from bus will be put into the register. When Ri in is equals to 1, the data available on the bus is loaded into Ri. Similarly, what happens when Ri out is 1? When Ri out is 1, the data from register Ri will be made available in the bus. So, the data from register Ri are placed into the bus. Now, you see, when this is 1, this is happening. When this is 0, what will happen? When this is 0, there will be no change. So, there will be, this signal will not get activated. So, nothing will happen, neither in nor out. Let us see this register transfer. So, similarly for individual register, we will be having some kind of signal like this. Let us say this is register R1 and this is register R2. So, for this register, one signal will be there Ri in, R1 in, that will make the data available from bus to this register, and there will be another signal Ri out that will make available the data from register to the bus. Similarly for R2 it is also there. For register transfer, move R1, R2. That means content of R2 should be available into R1. What needs to be done? Firstly, what we need to do is that content of R2 must be available in the bus. So, if I want the data of R2 to be available in the bus, which signal is required? R2 out. So, R2 out is required to be 1. So, how do we do it? Enable the output of R2 by setting R2 out equals to 1. So, if R2 out equals to 1, that means the data will be available in the bus. Now, enable the input of register R1 by setting R1 in equals to 1. Now, we also want that the data from the bus should be made available into register R1. In that case, what we need to do? The signal R1 in should be 1. So, for outputting R2 out, we require R2 out. For making available inside R1, we require R1 in. R2 out, R1 in. All operations are performed in synchronism with the processor clock. So, this particular operation, transfer, register transfer, it is within the processor, which is much more faster. So, the control signals are asserted at the start of the clock signal. After the data transfer, the control signal will return to 0. So, when the control signal will return to 0, what will happen? When the control signal is 0, no data will be available either on the bus or no data will be available in the register also. Only when that signals are activated, the data from either bus comes in into a particular register, or from a particular register the data goes into bus. So, and after the data transfer, as I said, the control signal will return to 0. So, we can write this particular, to perform this, what control signals are required in a particular step. So, at T1 we can perform R2 out, R1 in. R2 out will make available of the data of R2 into the bus, and R1 in at the same time will bring in the data from the bus into R1, which is happening in a time step T1. So, T1 equals to will be in T1 R2 out, R1 in. These are called control signals, and this is the time step where this particular control signals are activated. Let us see an ALU operation. So, for performing an ALU operation, add R1, R2. What needs to be done? Similarly, there are R1, R2. We need to make available both R1 and R2 in these two places. One is directly connected to the bus and another value is coming from this Y register through this mux. Please try to understand this. We need to add two values, two register values. We have those registers in place. One of the register output needs to be made available into one of the input of the ALU. Another register output needs to be available in another ALU output. And we must understand one thing, that we have a single bus. So, only one transfer can take place at a time. So, the first thing, bring the two operands R1 and R2 to the two inputs of the ALU, as I just now said. So, one will be coming through this Y and another can come from the internal bus. This is how the organization is made. So, this is how the data transfer will also be made. And finally, after this ALU operation, the result will be stored in Z and then it will be made available through this control signal into the bus and then it will move to R1. Now, let us see what are the various time steps, what control signals are required to be activated. So, in the first go, let us do what? make R1 available through Y. If we make R1 out and Y in, the data will be available in Y in. So, data from R1 through this bus comes in and it goes to Y using the control signal R1 out and Y in. Now, we have to make another signal available, that is R2 out. If we just do R2 out, we see that it is directly connected, it is not connected through any bus. So, at any point of the time, whatever is out here is directly available into one input of the ALU. So, it is directly available here. So, when we do R2 out, this particular value is directly available here. And in Y, R1 value is available. If we do select Y, then the Y value through this mux will come in and will be available to this input of the ALU. So, what we are doing here? We are doing R2 out, which is directly connected here. We are selecting Y using this mux. So, the value which is there in Y, it was R1, will come in through another input of ALU, and then we can perform the operation, because both the inputs are now available. We do add, and after adding, what we do? We do Z in, because we can directly make this input into this through this particular signal which is directly connected to the ALU. So, at T2 we are performing R2 out, select Y, add and Z in. So, now using this particular operation, the value is available in Z. Now, the Z contains the result, but where we need to store the result? In R1. So, for storing the result in R1, what we need to do? Now my value is available in Z. I do Z out, so the data will be available in the bus, and I do an R1 in. So, it will go in into R1. So, these are the 3 time steps that are required to perform this particular ALU operation. Let us move on. Now, we also need to fetch a word from the memory. So, for fetching a word, what is required? Let us see that. So, these are the following steps that are involved to fetch a word from memory. The processor specifies the address of the memory location where the data or instruction is stored. The processor requests for a read operation. For fetching, we are reading actually. The information to be fetched can be either an instruction or it can be a data. Accordingly, it is fetched. The data read is brought from MDR, from memory to MDR. We already know all these things, we have already discussed in previous classes. So, when we fetch an instruction or data, we put the address in MAR, we activate the read control signal. Once it is read from the memory, it is brought into MDR, and now from MDR, which is an internal processor register, we can move the data or instruction wherever we want it. Then it can be transferred to the required register or ALU. It can either go to IR if it is an instruction, or it can go to ALU for further processing if it is a data. Now, what happens for storing a word into memory? For storing a word, the steps involved is to, first is the processor specifies the address of the memory location where the data is to be written. Now, here the thing is different. You have to load the particular address of the memory where the data is to be written into MAR, and then you have to load the data that you want to write in that particular memory location into MDR. So, you have the data in MDR, you have the address where to be written in MAR, and the processor request for a write operation. So, the content of MDR will be written to the specified memory location. Now, let us see, this is the connection of MDR. Now, you already know that MDR is a register which is connected to the internal processor bus and it is also connected to the memory bus of the system. So, in this particular case, we require 4 switches. One, as it is connected to the internal processor bus, when we do MDR out, the value available from MDR will be made available through MDR out into this internal processor bus. And when we are doing MDR in, then the data from internal processor bus will be made available to MDR. As MDR is also connected to an external memory bus, we require 2 more signals. What are the 2 more signals? MDR in E, MDR out E. E stands for external. So, MDR in E means data available in the memory bus will be made available to MDR, and the data available in MDR can be transferred to the memory bus using MDR out E. So, whenever we are doing MDR out E, then the data from MDR may be available in the memory bus. So, these are the control signals that are required. Memory read-write operation, what happens here? The address of the memory location is transferred to MAR, as I have already said. At the same time, the read or write control signal is provided to indicate the operation. Once we put the address in MAR, we need to also specify whether it is a read or write. For read, MDR is not coming into picture initially, but for write, you also need to write that particular data, and for the read, the data from the memory will come into MDR. So, for read, the data from memory data bus comes to MDR by activating MDR in E, as I just now said. For write, the data from MDR goes to data bus by activating the signal MDR out E. So, these are the signals that are required for communicating with the external memory bus. So, when the processor sends a read request, it has to wait until the data is read from the memory and written into MDR. It is pretty obvious that the memory is slower than processor. Once the processor sends a read request, it has to wait for some time till the data is available in MDR. To accommodate this variability in response time, as there is no fixed response time, that how much time it will be required, the processor has to wait until it receives an indication from the memory that the read operation has been completed. Please try to understand this. For a read operation, what we do is we put the address from where we need to read into MAR, we activate the read control signal. Now, we really do not know at what time the data will be available, but the data will be available after some time. So, till that time the processor has to wait, but when the processor will know? When a signal will be available from the memory to the processor that yes, the memory function has been completed. So, a signal is required to be sent from the memory to the processor to know that yes, the data is now available in the particular register, in that particular MDR. So, to accommodate this variability in response time, the processor has to wait until it receives an indication from the memory. So, this indication is provided by a control signal known as memory function complete, MFC, is used for this particular purpose. Whenever memory function complete is provided, then we understand that now the data is available in MDR. Either way, for a write, you have put the data into MDR, the address into MAR, and you have activated the write control signal. Once the write is performed, it will inform. So, when this signal is 1, indicates that the content of specified location is read and are available on the data lines of the memory bus. Then the data can be made available to MDR, because it is directly connected to MDR. From the data lines of memory, it can be available to MDR. So, let us see what are the control steps, or what are the time steps that are required for this particular operation. Fetch a word, move R1, R2. R2 is a memory location. So, what we need to do? We have to put this particular memory location, R2 value, into MAR, and then we have to activate the read control signal. Once that is done, then we need to wait for a signal, that is MFC. We need to wait for memory function complete signal. Once that signal is available, then from MDR the value can be moved to R1. So, let us see what are the steps that are followed. R2 goes to MAR. We start a read operation on the memory bus, wait for the MFC response from the memory, load MDR from the memory, and then from MDR it is transferred to R1. So, let us see the steps. First we do R2 out and MAR in, because in MAR the address should be present, and we activate the read control signal. We perform all these things in one go, in one time step. After it is read, the data will be available in MDR. How it will be available? It will be available through this signal MDR in E, and we have to wait for memory function complete. Or the other way around, if you think that when wait for memory function complete, this particular signal will get activated from the memory, then automatically this MDR in E should be on, made available, such that the data comes into MDR, and once the data is available in MDR, it can be transferred to R2 through MDR out and RI in. So, these are the following steps which will be required. First, we are making R2 out, putting it in MAR using signal MAR in, we activate the read control signal. Then we make MDR in E available, activate this, and we wait for memory function complete. When this signal comes and this is already on, that means the data will be available in MDR. Once the data is available in MDR in this particular step, then we perform MDR out and R1 in. For storing a word, two things is required. One is that particular address where we need to store should be in MAR, and the data what we need to store should be in MDR. So, we are doing that. Here in this particular location, R2 must be stored. So, R1 should be in MAR and R2 should be in MDR, because R2 is the data which needs to be stored by the address pointed by R1. So, R1 goes to MAR, R2 goes to MDR. Start the write operation on the memory bus and wait for the memory function complete. Once the memory function complete, other operation can be taken care. So, in this case, we do R1 out, MAR in, R2 out, MDR in. So, in MAR the address is present, in MDR the data is present, we perform write operation, and then we do MDR out E and wait for memory function complete. Now, let us see the execution of a complete instruction. So, in this case what we are now taking a complete instruction. So, for executing a complete instruction, what is required? We need to first fetch that instruction. In the same way, we need to put the content of PC into MAR, we need to activate the read control signal, at the same time we have to increment the PC value, and then we have to wait for memory function complete because we have performed a read. Once it is done, and then the data which is present will be brought in through MDR, and then from MDR it will go to IR. So, we have to fetch the instruction in this particular case. So, for fetching the instruction, let us see what steps are required. So, we do PC out, content of the PC stores the address of the next location that is to be executed. We do PC out, MAR in, we activate the read control signal. At the same time, we select 4, because once you do PC out, it is available in the input of the B input. So, once we do, so this particular diagram is not the entire single bus architecture, but let us say you have PC here in that. So, when you do PC out, that means it is available in this bus, and from this bus it is directly connected to one input of the ALU. So, it is available here. Once you do PC out, it is automatically available here, and then you are putting that address in MAR, activating the read control signal, and at the same time we are doing select 4. We are selecting 4. If we select 4, then this particular input will have 4. So, this is having PC out and this is having 4, and we do an add, and then after adding we put the value in Z in. So, that means in Z now you have the incremented PC value. What needs to be done to this PC value? This PC value needs to be transferred to PC again. That we will be doing in the next step. So, in this particular step we are putting the value of the particular PC, whatever value in the PC, into MAR. We are activating the read control signal. Through this select, we are selecting 4 such that in the ALU 1 it is PC, 1 it is 4. Now, we add it, put it in Z, and next we do Z out and PC in. Now, PC contains the incremented value, that is PC plus 4 we have done through ALU. We are also doing Y in. Why we are doing Y in? We will be seeing it for the case of branch instruction, that it is required. And then we are, as we have done read operation here, in the next we need to wait for memory function complete. For this particular signal, we need to wait from the memory to come. Once this is asserted and this is performed in T2, then the data is available in MDR out. Now, you see we are not giving MDR in E here. You can give, but this is obvious that that is also there, MDR in E. So, we are doing wait for memory function complete. Once this is performed, MDR out we perform, because the instruction read pointed by PC is now available in MDR. We are transferring that to IR. We are doing MDR out and IR in. That means in these 3 steps, what we have done? We have just fetched the instruction from memory. Now, what we need to do? We need to execute that instruction. For executing that instruction in the same way, you have to bring R1 into one of the input of the ALU and R2 into another input of the ALU. So, we have already performed these steps for an example previously. We do R1 out, Y in. So, R1 is made available through the bus to Y, and we do select Y. Similarly, we do R2 out, which is directly connected to ALU, and then we do add. As this is already selected, so we perform add here and then we perform Z in. So, the output of R1, R2 is present in Z. Finally, it has to be brought into R1. So, we do Z out and R1 in. So, for executing a complete instruction, part of which we already knew it. So, this is only fetch phase. So, every instruction will have these 3 steps in common for single bus architecture. Let us move on with the 3 bus architecture, where we will be performing with operation sub R1 comma R2 comma R3. So this will be minus. So R1 will be R2 minus R3. So in this particular case, same way we need to fetch from memory, and this is the bus organization now. So PC has got an incrementer, and from this register one input goes to A, another input goes to B. The input which goes to A, it has to come through this mux and made it available to the A input of ALU, and another input is directly connected. So one input when we do out, which is directly connected to the B input of ALU. So taking into this architecture, now we will execute this particular instruction. So first we do PC out, R equals to B. So R is a signal we are making, R will be equals to B. We do MAR in. So basically PC out, when we do, it is available through the PC out, which when we do, it is available through B bus. So as it is available through B bus, so it will be available through this B input. So R equals to B, MAR in, read and increment PC. Here instead of putting it somewhere, there is an incrementer circuit inbuilt, so we are performing it in one go. In any case, if we have performed MAR in, we have to wait for memory function complete. We are waiting for memory function complete. Once this signal is available to the processor, then in MDR the data will be available. And we do MDR out B, R equals to B and IR in. Let us see this. We do MDR out B. So MDR out can be made available to A, also to B, but we are making MDR out B, then R is equals to B, and through this R it is going to IR in. So this is the path which it is following. We are doing MDR out B, and then we are doing R equals to B. Now R equals to B means the B value through this R will be made available to C bus, and from this C bus the data will go into IR. Now these three steps are required to fetch the instruction. Now to execute the instruction, as we already know that two registers can be read simultaneously and one register can be written simultaneously. So two register read and one write can be performed simultaneously. Similarly, for this instruction we require something like this. We need to read the value from R2 and R3, and we have to write the value back in R1. So what we are doing? R2 out A. So R2 out will be available to A bus, R3 out B, it is available to B bus. We need to select A because it is connected, the A bus is connected to a mux. Then we provide the operation that needs to be performed, that is sub, and then at the same time we do R1 in. Two different reads and one write is performed in one particular step, and finally end. Let us see this, what we are doing. We are doing R2 out, we are doing R2 out A. So from this register file we are doing R2 out A, then R3 out B. B is directly connected, no problem. As A is connected to this mux, we are doing select A. So it is connected, we are performing sub and we are doing R1 in. That is what we are doing. R2 out, R3 out, A and B, select A, sub and R1 in, and finally we end. So what we can see that for performing the same operation earlier we were requiring 3 steps. That 3 steps is now reduced to one single step. In one single step we are able to perform this sub operation or any ALU operation, because at the same time we are reading from 2 register and writing into 1 register. So, we have come to the end of this lecture, and in the next lecture we will be looking forward to the various other instructions, how we can execute various other instructions. Thank you.